Okay, so let's continue from where we stopped yesterday. Okay, yesterday we discussed about how is it that the transformer can function. Okay, the basic working principle of the transformer. How is it that the transformer can function? Why is it that it can only work with alternating current? And how is it that it can increase the voltage or decrease the voltage? Okay. So today we will continue a little bit. Okay. So we know that transformer, there are step up transformer and step down transformer. So how is it that we can identify which is step up transformer, which is step down transformer? So again, it's very simple. We look at the number of turns of the primary coil and the secondary coil. If the secondary coil has more number of coil than the primary coil, then it is a step up transformer. If the secondary coil is less than primary coil, then it will be a step down transformer. Okay, next we want to look at this one, the electronic symbol. Okay, the electronic symbol of the transformer. So actually, if you look at these two symbols for step up transformer and step down transformer, they are actually the same symbol. Only you flip it left and right only. Okay, you only flip it left and right. So basically, the transformer, you can use the same transformer as step up transformer and step down transformer. Okay, the same transformer, you can use it as a step up. You can also use it as a step down. So for example, okay, we have a transformer. Okay, so this is the power source, alternating current supply. Okay, alternating current supply, and this is the load. So since this coil is connected to alternating current supply, so obviously this is primary coil, and then this is connected to the load, so obviously this is the secondary coil. And the secondary coil have more coil than the primary, so obviously this is a step up. However, if you want to convert this into step down, it's very simple. Actually, all that we need to do is just change the actually we just need to switch the power source to the other coil. And then the load, we just connect to the opposite side. Then you see this one, because it's connected to the power supply, so that means this will be the primary coil. This one connected to the load, so that means this will be the secondary coil. So now you see the secondary coil become less, the number of turns in secondary coil become less than the primary coil. So this become a step down transformer. So that will be the same for the symbol of the electronic symbol also. So for example, this is the electronic symbol of a transformer. Okay, so if this one connect to power supply, this one connect to a load, then this will become a step-up transformer. Because this is the primary coil, this is secondary coil. However, if you just flip it, same thing. Okay, you just change side only. This side connect to the power source. This side connect to the load. Then the step-up transformer will become a step-down transformer. So the same symbol, you can just flip it around and then you can, and then it will become a step-up transformer or a step-down transformer. So actually it is very simple, okay? It's very simple. Okay. So let's look at a few examples. Okay, let's look at a few examples. So let's look at this example number 1. A figure shows a 40-volt bulb connected to a 240-volt power supply through a transformer. Find out the number of turns of the secondary coil that is required for the bulb to light up at normal brightness. Okay, so we want to find out this is how much the number of turns in the secondary coil. So very simple. Voltage primary over voltage secondary equals to the number of turns in primary over number of turns in secondary. Okay, so for your information, this equation, there is no rule that says, oh, it must be prime voltage secondary voltage on the left side, number of turns on the right side. Or the primary must be on top, secondary must be at the bottom. Okay, it can be anywhere, it can be any arrangement. You can write like this also can. You want the number of turns on the left side also can. You want the secondary on top also can, no problem. Okay, can see that? Okay, it doesn't matter. It can be the voltage on the left, okay, or the number of turns on the left. It can be the secondary on the top or the primary on the top. Okay, also can, because it's the same thing. Okay, they are the same thing. Because the concept is that the ratio between the voltage of the primary coil to the secondary coil and the ratio is the same as the ratio of number of turns in primary coil to the secondary coil. So this equation is written based on that concept, okay, based on that idea. So as long as the ratio is the same, then no problem. Okay, you can write in any way you want. Okay, any way that is more convenient or can help in your calculation. No problem, Okay. So the voltage in the primary is this one. This is the primary voltage because this is the power supply. So 240 volt. Secondary, 40 volt. Number of turns in the primary coil, 120 turns. So how many turns in the secondary? Okay, so you get 20 turns. Okay, 20 turns in the secondary. Alright. They are very simple. Actually this calculation you also got learn during the lower form science. Okay, next number 2. Figure show a circuit diagram of a transformer in a mobile phone charger. Oh, and you see, actually the symbol, okay, the symbol for the transformer. You see, it is not necessarily like, okay, this one is, you must have like 4 loop or you must have like 3 loop. As long as one side is more loop than the others, okay, than the other, then it's already, that will show that it is the symbol of transformer. Okay, so A, calculate the number of turns in the primary coil. Okay, so this is what we want to find, a number of turns in the primary coil. So, number of turns in primary over number of turns secondary equal to voltage in primary over voltage in secondary. Alright, so number of turns in the primary is the one that we are looking for. So number of turns in secondary is 10. Voltage primary 240. Voltage secondary is 5 volt. Okay, this is output lah. So 5 volt. So number of turns in primary coil is equal to 480 turns. Okay, so because number of turns is number of turns, so there is no unit lah. Okay, you do not have to write 480 turns or 480 coil. Okay, there is no unit for number of pins. All right, next is B. Is the transformer in the mobile phone charger a step up or step down transformer? So obviously this is step down. Okay, step down transformer. Explain your answer. So why is it that you say this is a step down transformer? So obviously the secondary voltage or the output voltage is lower than the input voltage. Okay, so for example, output voltage lower than input voltage. Okay, so there are a few answers that is acceptable for the explanation. You can say output voltage lower than input voltage. You can say voltage in secondary coil lower than the voltage in primary coil. You can also say number of turns in secondary coil less than number of turns in primary coil. Also can. Okay, there are a few explanations that are set. Okay. So until here, any question? Anybody got any question until here? Okay, thank you very much for responding. Okay, thank you very much. I see the number of people that attend today's class is less than yesterday lah. So I hope the number will increase at least same as yesterday or more than yesterday. If today is less than yesterday, then that means later tomorrow going to be less than today, and then going to be less and less. And then at the end, I will be talking to myself. Okay, I hope that doesn't happen. Okay, I hope you all will try your best to attend. Okay, yeah, maybe enjoying your holiday. Okay, I'm actually enjoying myself also right now. Okay, teaching physics. This is my holiday. Okay. All right. Okay. No, I'm not crazy. Sorry. Okay. Okay, so let's continue. All right, let's continue. Ideal transformer. What is an ideal? Okay, wait, because some part is missing. All right, ideal transformer. So what is an ideal transformer? So an ideal transformer is a transformer that does not experience any loss of energy. So basically the meaning of the word ideal is that it is perfect lah. Okay, ideal that is like is perfect. So a perfect transformer is a or an ideal transformer is a transformer that does not experience any loss of energy. So if it does not experience any loss of energy, that means all of the energy that go into the primary coil or the primary circuit will come out in the secondary circuit. So for example, every 1 second, 100 joule, okay? Let's say every 1 second, 100 joule that is supplied by the power supply go into the primary coil, and the secondary coil also can come out every 1 second, 100 joule. Then this will be perfect lah. That means no energy is lost in the process when the energy is being transferred from the primary coil to the secondary coil. So this is what we call an ideal transformer. So efficiency of transformer can be calculated with the output power over the input power. So you see here we say that it's the power because um, we don't say like energy okay, we say power because when we on because the total energy that is transferred depend on how long you on the transformer right now. Okay, the total amount of energy that is transferred. Okay, depend on how long lah. The longer you on the transformer, the longer you use the transformer, then that means there will be more energy. So that is why we discuss this in terms of power. Okay, so power is rate of doing work or rate of using energy lah. So for example here, I say 100 joule per second. Okay, every 1 second 100 joule. So if every second 100 joule go in, every second 100 joule come out, then that means no power is lost, no energy is lost. Okay, so output power over input power times 100%. That is how we calculate the efficiency of a transformer. And the symbol for efficiency is if I remember correctly, this is the symbol of mu. Okay. So the efficiency of ideal transformer is 100% because the output power is the same as the input power. Okay, so efficiency is 100%. Okay, now one thing that is very important here is that if the output power equals to the input power, then that means the voltage, the primary voltage times the current in the primary circuit. Okay, voltage in the primary circuit times the current in the primary circuit will be equal to the voltage in the secondary circuit times the current in the secondary circuit. Okay, why? Because power is equals to voltage times current. So if the output power equals to the input power, then the voltage times current of both sides of the primary and the secondary will be the same. So this is output power. So actually this one should be secondary lah. Okay, this one actually should be secondary. Actually the same lah. Okay, just click on it lah. It's the same thing. Output power is voltage secondary times current secondary. Okay, output power. Input power is voltage primary times current primary. It's the same thing. I just flip it over. Okay. Alright, so this will be the case if this is an ideal transformer. Okay. Okay, so let's look at some example. Okay, a transformer that is connected to a 240-volt power supply supplies 27 watt of power at a voltage of 18 volt to an electronic equipment as shown in the figure, assuming the transformer is ideal. So it says assume that the transformer is ideal, so that means that there's no power loss. That means the power in equals to the power out. That means the power in the primary equals to the power in the secondary. Okay, so A, calculate the number of turns of the primary coil. So this is what we want to look for. So we number of turns in primary over number of turns in secondary equals to voltage in primary over voltage in secondary. So number of turns in secondary is 60. And then voltage of primary is 240 volt. Number of voltage in secondary is this 18 volt. Okay, this is the output, 18 volt. Okay, so number of turns primary equals to 800 turns. Okay, equals to 800 turns. Huh? All right, after that, let's look at B. Calculate the current in secondary circuit. That means you want to calculate the current that flow here. Okay, calculate this current. So you see in the secondary circuit here, we have the voltage, we have the power. So that means we can calculate the current here. Power equals to voltage times current. So the power is 27 watt, voltage is 18 volt. So the current can be calculated. And we get 1.5 ampere. And then C, calculate the current in the primary circuit. Now we want to find out the current in the primary circuit. Okay, however, you see the current in the primary circuit, we do not have the power. We only have the voltage only. So how to count the primary current? This is where the assumption that transformer is ideal come in. If the transformer is ideal, that means this power here and this power is the same. Okay, because no power loss. So power in the both sides is the same. So if this side the power is 27 watt, so that means this side the power must be also 27 watt. So power equals to voltage times current. Okay, power is 27 watt. The voltage is 240 volt times the current. So the current will be 0.1125 ampere. Okay, 0.1125 ampere. Okay, okay, done. All right. So from this example, there's something that I want to point out. You see, when the transformer decrease the voltage, when you see the voltage from 240 volt decrease to become 18 volt, and then you see that the current in the primary at first is 0.1125 ampere. But when the voltage go down, what happened to the current is the current go up, become 1.5 ampere. You see or not? When the voltage go down, the current go up in transformer. This is the opposite of what we learned in Ohm's law right now. This is the opposite of what we learned in Ohm's law. In Ohm's law, V equal IR. When the voltage go up, the current will go up right now. Okay, when the voltage increase, the current will increase. For example, what we learned in Ohm's law, let's say we have a battery and a bulb. So let's say this bulb is 1 ohm, this battery is 1 volt. So how much is the current? V equal IR. 1 volt, 1 ohm, current will be 1 ampere. Okay, so we see this is 1 ampere. Okay, let me show this. Now this is very important to understand the working and the importance of the transformer, okay, in the application also. Okay, so you see, in Ohm's law, we learned that, okay, you see here, when the voltage is 1 volt, the resistance of the bulb is 1 ohm, and then the current is 1 ampere. Okay, now, let's say that we put 2 batteries. The bulb is still the same, 1 ohm. But because we put 2 and connect in series, so it becomes 2 volt. So how much will be the current? Okay, so if we calculate V equal IR, this one is 2 volt, resistance is 1 ohm, so the current will be 2 ampere. Okay, can see or not? You see 1 volt, 1 ohm, 1 ampere. 2 volt, 1 ohm, 2 ampere. So that means the current go up. Higher voltage, higher current. This is very logical right now, because when the voltage increase, that means the energy, okay, the work done to drive every 1 coulomb of charge increase. So logically, every coulomb of charge get more energy, then it should move faster. If it move faster, then the current should increase. The charge move faster, the current should increase. So why is it that in transformer, when the voltage go down, the current go up? Okay, and the opposite also same. That means if this is a step up transformer, that means if we increase the voltage, what will happen is the current will go down. Okay, if this is step up transformer, from low voltage to become high voltage, then the current will go from big to small. Okay, so why is it that in the transformer it is the opposite of what we learned in Ohm's law? The reason is inside the power. Okay, the reason is because of the power. You see, in the case of a battery, let's see how much power do the bulb get. Okay, let's see how much power do the bulb get. For this case, power is voltage times current. So this bulb, the voltage of this bulb is 1 volt, the current is 1 ampere. So that means this bulb get 1 watt. 1 watt means every 1 second get 1 joule of energy. Now that we increase the voltage, we put 2 batteries. What is the power of this bulb? Power is voltage times current. Voltage is 2 volt, current is 2 ampere. So that means now the power of the bulb is 4 watt. Okay, 4 watt. So that means 4 watt means that the bulb get 4 joule of energy every 1 second. So you see the energy increase or the energy supply increase or the power increase when the voltage increase in this case. You see or not? So this is the reason why the current can increase according to the increase of the voltage because the power can increase. However, in transformer, if this is ideal transformer, the power in the primary and secondary is equal, is the same. That means the power already fixed. The power cannot increase. You see or not? If we increase the voltage, the power is still the same. We decrease the voltage, the power also the same. So that means because the power cannot change, so the when the voltage increase, the current will go down. When the voltage decrease, the current will go up. Okay, so let's see. Okay, let's say that let's use this same example. Okay, you see power is voltage times current, right? But because the power is fixed at 27 watt, cannot change. So what happens is when the voltage go down, then the current must increase up. You see or not? From this equation, we can see if the voltage go down, the current must increase so that the power remain the same, 27 watt. So same thing also. If the power is fixed already, cannot change. So when the voltage increase, the current will go down. So that is the same 27 watt. Can see or not? Okay, get the idea. Okay, the power is already fixed. This power 27 watt come from the primary coil, come from the supply in the primary coil. So if the primary coil supply 27 watt, then the secondary will get 27 watt only. That is all that the secondary coil get, 27 watt. If the primary supply 100 watt, then the secondary will get 100 watt like that. So it cannot, the power will not be able to go up or go down because whatever changes in the secondary will not affect the primary. Understand? Okay, but you change the number of coil in the secondary. Okay, to change the voltage in the secondary, but the energy supply comes from the primary. So it's already fixed. Whatever you make, whatever changes you make in the secondary, it will not affect the primary. That means it will not able to make the primary supply more power. Okay, the power in the primary already fixed. Okay, get the idea. So the power in the secondary depend on how much power that is supplied from primary. So when you change the voltage in the secondary, then the current has to change. Okay, according if the voltage go up, current has to go down. If the voltage go down, the current has to go up. Okay, get the idea. So I explain this. Okay, I take some time to explain this because usually students have problem when it comes to transformer. Because we learn in Ohm's law that voltage up, current up, but suddenly come to transformer, voltage up, current down. So it makes a lot of students confused. And when a lot of students confused, the student will also doubt. Okay, they suddenly they got mixed up. They're very confusing. So even the original Ohm's law that they learned, also they get confused. They don't know which one is true, which one is correct, which one is wrong, or something like that. So so I take some time to explain this. Okay, this is very important. I hope that by explaining this can clear up any confusion. Okay, so until here, anybody got any problem? Got any question? Okay, thank you very much. Okay, thank you very much for responding. Huh? Okay, so continue. Okay, let's continue on to the next example. Okay, number 2. Figure show an ideal transformer used to supply power to two 12-volt, 24-watt bulb at their rated power. If the voltage of the electricity supply is 240 volt and the current in the primary coil is 0.2 ampere, what is the current in the secondary coil? So they want us to find out the current in the secondary is how much. Okay, so you see, although they got give us the voltage in the primary coil and current in the primary coil, but actually we do not need this information to calculate the current in the secondary coil because here they already give us the power of the secondary coil. Okay, they say that this bulb is 24 watt, right? Okay, 12 volt, 12 volt, 24 watt, 24 watt. And it says here that ideal transformer used to supply power to two 12 volt, 24 watt bulb at their rated power. What does it mean by at their rated power? When it says that, okay, it supply power to the bulb at their rated power, it means that the two bulb get the 24 watt that is labeled on the bulb. Okay? If the bulb can get 24 watt, this also means that the bulb can get 12 volt lah. Okay? So with this information, we can already calculate the current of the secondary coil because power equals voltage times current. So the power in the secondary coil is 24. So 2 times 24. Okay. Voltage in the secondary 12. In series, you see, these two bulbs is in series. So if the two bulbs can get 12 volt, so that means the total must be 24 lah, or 2 times 12. Okay, the voltage. So how much is the current in the secondary coil? Okay, it will be 2 ampere. Okay, so this is one way to calculate, or another way to calculate is we use the information that is given for the primary coil lah. Okay, I give you alternate method. Okay, another way is because the power in the secondary and power in the primary is the same because this is ideal transformer. Okay, if you got say ideal transformer, then only we can calculate like this. So the voltage primary times current primary equals to voltage secondary times current in the secondary. So voltage in primary is 240, current in primary is 0.2. Voltage in secondary, volt, so 2 times 4. Current in secondary is how much? Okay, so also get 2 lah. Okay, also get 2 ampere. So you see, it's the same thing lah. Okay, so there are 2 methods for us to solve this question. Okay, let's look at number 3. A transformer is used to lower the electrical supply voltage of 240 volt to supply power to about with a rated power of 12 volt 24 ampere. If the current in the primary coil is 0.15 ampere, what is the efficiency of the transformer? Okay, they want us to calculate the efficiency of the transformer. Okay, so how to calculate efficiency? Efficiency is power output over power input times 100%. So how do we calculate the power output? That means we take the voltage in the secondary times the current in the secondary. Okay, I write out the equation first. Voltage secondary times the current in the secondary. Because power equals voltage times current. Okay, power input is voltage in primary times current in primary times 100%. Okay, so efficiency will be equal to, okay, voltage secondary 12, current secondary 2 ampere. Okay, voltage in primary 240, current in primary 0.15 times 100. So yeah. Okay, we get 66.67% of efficiency. Actually, this is very bad. 66.67% for transformer is actually super bad. Nobody want to, if your company make this kind of transformer, I think nobody want to buy. Okay, nobody want to use your transformer because this is very terrible. Okay, from what I know, the transformer in the market that is being used, I think the worst transformer also around like 80% like that. Okay, the worst is also around 80%. If your transformer is like lower than 80%, really nobody want to use. Why? Not only that, the transformer is wasting a lot of energy, and it will be also very dangerous also. Why? Why very dangerous? If the efficiency is low, then the transformer will be very dangerous. Very good now, very good. Because it will be hot. Okay? Because you see, if 66.67% go to the secondary only, then that means what? You have like 33.33%. 33.34% change to heat energy. Then that means your transformer will be extremely hot. Understand? Transformer will be very hot. So when it's very hot, then that means what? Accident can happen. It can melt the power outlet. It can melt the wire can melt, the casing of the transformer can melt, and so on. So can catch fire. So very dangerous. Okay, so usually from what I know, 80% is the minimum. But usually the good one is like 95 to 98% like that. I think. Okay, 95 to 98% is the good one. You can also see if you got use a handphone of different brand. For example, you got use Samsung, you got use Oppo, and then you got use like Yes. You know, yes, the phone company also got the service provider also got handphone. You will find that the charger, when you charge your phone, the temperature will be different. Some of them will have higher temperature, hotter than the other. I'm not going to say which company the charger will be higher temperature than the other, because I'm going to put this video in this recording. I will put in YouTube, so I don't want to get sued. Okay, I don't want people to sue me. So to say that I talk bad about their their brand. Okay, so if you got used before, then you yourself you know lah. Okay, I got used different brand phone, and I find that some of the charger is higher temperature than the other lah. Okay, so this tells you the quality or the efficiency of the transformer in the charger. All right. Okay, so let's continue. Number 4. Okay, a transformer is used to supply power to two 12-volt 24-watt bulbs which are connected in parallel. The voltage of the electrical supply is 240 volt and the efficiency of the transformer is 96%. Okay, so A, the number of turn on the secondary coil if the number of turn on primary coil is 900. Okay, we want to count up the how many turn on the secondary coil if the number of turn on the primary coil is 900. All right. So we want to count the secondary coil. Okay, so number of turn in the secondary over number of turn primary equals to voltage secondary over voltage primary. Okay, so number of turn in primary 900, voltage in secondary. How much is the voltage in secondary? You see, transformer used to supply power to two 12-volt bulb connect in parallel. It connect in parallel, so that means the voltage in the secondary is 12 only lah. Okay, because they are connected in parallel, so that means both of them get same voltage. Okay, if the secondary coil is 12, then both of them will get 12. Okay, so over the voltage in primary, which is 240. So number of turns in secondary equals to 45. Okay, 45 turn. Okay, B. The current in the primary coil so that the bulb is lit normally. Okay, you see this word is very important. It says that so that the bulb is lit normally, that means the bulb get 24-watt power. Okay, that means the bulb get 24-watt power. Okay, so the efficiency of the transformer is 96%. Okay, this is very good lah. Okay, 96%. All right, so how much is the current in the primary coil so that the secondary coil can the bulb in the secondary coil can get 24-watt of power. If get 24-watt of power, then the bulb is lit normally lah, can function normally. All right, so efficiency equals to power output over power input times 100%. So the efficiency is 96%. Power output, that means is the power in the secondary coil. You see, it says that there are two bulbs. Each bulb 24 watt, so that means the power output must be 2 times 24. Okay, because it says that the bulb is lit normally, that means the bulb get 24 watt. Okay, one bulb 24, two bulb 2 times 24. Okay, over power input. Power input. So voltage in the primary times the current in the primary. So the voltage in primary is 240. So current in the primary, this is the one that we are looking for. Current in the primary coil. Okay, times 100%. So solve this to find current in the primary. Okay, so the current in the primary is 0.2083 ampere. Okay, 0.2083 ampere. Remember the number of decimal place is minimum is 2 decimal place. Okay, minimum is 2. All right. So, any question until here? Anybody have any problem? Any question? Okay, thank you very much for responding. Thank you very much. Okay, your response is very important. Because if you respond, then I know that I'm not talking to myself. Okay, thank you very much. All right, so next. Okay, now energy loss and ways to increase the efficiency of a transformer. Okay, this part is extremely important. This part is extremely important because this part usually like to come out in essay question, like to come out in essay where they ask you to like modify the transformer so that it have a better efficiency, or they ask you to choose which transformer is the best one, or KLMN for transformer with different features. Ask you to choose the best one. Those kind of essay question Okay, understand the kind of question that come out in section B or section C. So they like to come out this kind of the question that you need to have the knowledge of this part. Okay, so just now we learned that an ideal transformer is a perfect transformer so there's no energy loss. However, we know that there's nothing perfect in this world. Okay, in this world there's nothing is perfect. And just now in the few example, we also got see a few questions where the efficiency is less than 100%. So those transformer with efficiency less than 100%, it means that the transformer is not ideal. Okay, it's not perfect, and there are energy loss. So what are the costs of the energy loss, and how do we minimize the energy loss? Okay, so let's look at the first one. The first cause of energy loss is the resistance of the coil. It is very straightforward. We know that the wire, the coil have resistance. So if have resistance, so that means work when the charge want to flow through the coil, the charge have to do work to overcome the resistance in the coil. The higher the resistance, the higher the amount of work that need to be done to overcome the resistance. So the work done to overcome the resistance in the coil will convert the electrical energy into heat energy. So the coil will become hot. So how to minimize the energy loss? Of course, to reduce the resistance of the coil. So how to reduce the resistance? We look back at what we learned previously about resistance. What are the factors that can affect resistance? First is length of the wire runner. Second is the cross sectional area of the wire. Okay, length of wire, cross sectional area of wire, and the third one is the resistivity of the material. Resistivity of the material. So can we so we can say that we use a thicker copper wire Why we say use thicker? Okay, thicker here is bigger cross-sectional area. So if the cross-sectional area of the wire is bigger, then the resistance will be lower. And then it says copper wire. Why? Because copper have low resistivity. Okay, so you see here, it doesn't say use thicker copper wire with shorter length. Why you only say thicker and copper wire, but doesn't say that we use a wire with shorter length? Why don't say it's shorter? Because not suitable for this application. Not suitable for application in transformer, right? You just think logically. In a transformer, you need um, primary coil, secondary coil with a certain number of turns, right? So that means there is not much you can do to make the length become shorter. If you make the length become shorter, that means you have less number of coil, right? So length, so by saying that you use shorter length is not how you say that, not practical, not practical for transformer. Understand? So this is very important. When we answer question, we have to give answer that is practical, that is suitable for the situation. Okay, for the situation, for the application, for the that can really help to solve the problem lah. That means we cannot just blindly give any um, explanation or any solution that is not practical. For example, quite a lot of students they just say or use shorter wire, shorter the length because they did not think about the practicality uh, in the context, okay, in the application of the transformer, okay, of the length of the wire in the transformer. So if you say you give use shorter length, that answer cannot be accepted, okay, because it's not practical. Okay, so that is the first one, resistance of coil. Okay, next is eddy current. Okay, what is eddy current? Okay, it says here the changing magnetic field induce eddy current in the iron core. The eddy current heat up the iron core. Hot iron core release heat energy to surrounding. Okay, basically, we know that when we have a conductor exposed to changing magnetic flux, then inside the conductor, you will have induced EMF, right? That is how the current in the secondary coil is produced, or the EMF in the secondary coil is produced by exposing the secondary coil to changing magnetic flux, right? Okay, by exposing the secondary coil to changing magnetic flux, EMF can be induced in the secondary coil. Okay. However, the core of the transformer, this piece of metal, the core of the transformer itself is also conductor. That means when the primary coil produces the changing magnetic flux, the core of the transformer is also exposed to the changing magnetic flux. So that means inside the core of the transformer will also have induced EMF. And the induced EMF in the transformer core will produce induced current in the transformer core. So that induced current we call eddy current. Okay, we call it eddy current. So when you have current, that means the charge is flowing. Okay, charge is flowing inside the transformer core. So when the charge is flowing, that means the charge have to do work to overcome the resistance in the transformer core, and the result is the work done will convert energy into heat energy. So it will heat up the transformer core. Okay, so energy is lost, energy lost as heat. You see that? So how do we solve this problem? How do we reduce the eddy current? From Ohm's law, when from Ohm's law, V equal IR, when the resistance go up, current will go down, right? Current will go down. So that is what we do, right? What we do is we try to increase the resistance of the transformer core. You see, previously when we look at transformer, it is like the transformer is the whole lump of metal, right now. Okay, it's like a whole lump of a big chunk of metal like that. Okay, a big chunk of metal. So if it is a big chunk of metal, then that means the cross-sectional area will be very big and the resistance will be very low. So how do we increase the resistance? We make the transformer core by using thin iron sheets. Okay, thin sheets of iron. Okay, thin sheets of iron, and we glue them together with insulation glue. Okay, glue them together with insulation glue. So we call this laminated iron core. Okay, so you can see from this picture that the core consists of thin sheets of iron. Okay, thin sheets of iron all stick together. Okay, so the glue is insulation glue. So that means every piece of the iron, they do not conduct. Okay, they are not conducted. There is no electricity can flow out between them. You see or not? So if you use thin sheets of iron, so that means you can decrease the cross-sectional area and increase the resistance. When the resistance increases, the current will go down, and in this case is the eddy current. The eddy current will become smaller. Okay, can see or not? Okay, so let me reduce how to solve this problem or how to reduce the eddy current. We say that we use laminated, usually laminated iron core, or if the material is soft iron, then we say that we use laminated soft iron core. Okay, like that. So we can reduce the eddy current. All right. Next is hysteresis. Okay, so what is hysteresis? Hysteresis. Okay, sorry. Hysteresis is, okay, you see, the iron core is magnetized and demagnetized continuously by the changing magnetic field. The energy supply for magnetization is not fully recovered during demagnetization. The difference in energy is transferred to the iron core to heat it up. So we can call this as the hysteresis lah. Okay, basically what happened is when the, you see, when the alternating current flow in the primary coil, the magnetic flux, okay, magnetic flux flow through the iron core, right? Okay, the magnetic flux flow through the iron core. So actually what happened is when the magnetic flux pass through the iron core, it will cause the iron core to become magnetized. That means the iron core itself changed into a piece of magnet. Okay, the iron core itself turned into magnet. And when it turns into magnet, that means the iron core itself can produce magnetic field. Okay, produce magnetic flux also. So that magnetic flux that is produced can make the magnetic field become stronger. Okay, can make the magnetic field stronger. Okay, now, however, how is it that you can magnetize the iron core actually? How is it that you magnetize? Basically, the way that you magnetize is the flow of the magnetic flux make the electron that orbit around the atom of the iron orbit in the same direction. And electron have charge, right now? Electron have charge. So that means when the electron is orbiting in the same direction, then the combined magnetic field that is produced by the electron, the flow of the orbit of the electron, will produce a strong magnetic field. So that means the core, okay, the iron core itself changed into a piece of magnet. Basically is like this lah. Okay. Inside the iron core, there are atoms. Okay, these are atoms of the iron. Okay, we have electron orbit around the iron. Okay, some orbit in this direction, some orbit in this direction, some orbit like this. Okay, in different direction right now. Okay, they all orbit randomly in different directions. So electron have charge, right now. So actually, when the electron is when the electron is flowing, it's orbiting, that means the electron is flowing, right now. If the electron is moving, that means charge is moving. If charge is moving, that means you have current, right now. You have current. And when you have current, the current will produce magnetic field, right now. Okay, current will produce magnetic field. But because the electron all orbit randomly in different directions, so the magnetic field that they are produced, magnetic field that are produced by the electron, they all like they cancel each other off like that lah. Okay, they cancel each other off like that. So they do not combine together to become a stronger magnetic field. However, when you have a magnetic field pass through them, a strong magnetic field, okay, that is produced by the current, pass through them. What happens is the magnetic field influences them. It makes the electron that orbit in different directions all become orbit in the same direction. So when they all orbit in the same direction, then the combined magnetic field that they produce will become stronger. So that means it makes the iron core itself become a magnet. So we say that the iron core is magnetized. However, this magnetic field or this magnetic flux is produced by alternating current right now. That means the magnetic flux will become strong and then weak and then become zero and then become stronger again but in the opposite direction. So what happens to the electron is it rotates, it orbits in one direction and then slow down, stop, and then change to the opposite direction. You see or not? So every time the current change direction, this magnetic flux also change direction. So it makes the electron change direction, become faster, slow down, stop, change direction, become faster, stop, slow down, change direction, become faster, stop, slow down. So you see, so all of these need energy. You imagine you want to make the electron, you want to force the electron all orbit in the same direction. Make it stop and then force it to orbit in the opposite direction. All of this needs energy. So all of this energy to magnetize and demagnetize the iron core will release heat energy. Heat energy turn into heat energy. You see, so this effect actually is not exactly hysteresis, okay, but we call this hysteresis. Because hysteresis actually means the lagging, okay, the lagging of the magnetic field. Okay, for example, what the hysteresis means actually is that, for example, okay, this magnetic flux flow this direction, and then it takes a while. It needs some time, then only the core of the transformer can be magnetized. But when the core of the transformer is magnetized, this magnetic flux change direction already. So you have to wait a while, wait some time for the core of the transformer to become demagnetized and magnetized again in the opposite direction. So there is a lag. There's a lagging behind between the magnetized and demagnetized of the transformer core and the changing of the magnetic, changing direction of the magnetic flux. Okay, so this lagging, the hysteresis actually refers to this lagging, but this lagging, it causes the heat energy to be produced, okay, cause the heat energy to be produced. So it's a problem, it's a problem that causes the transformer to become inefficient, loss of energy as heat. Okay, so how to solve this problem? We use material that is easier to be magnetized and demagnetized. So we use the soft iron as the core of the transformer. Okay, we choose the soft iron as the core of the transformer. Why? Because soft iron require a smaller amount of energy to be magnetized. That means you don't need that much energy. The amount of energy that need to magnetize and demagnetize is less. Or you can also say that the soft iron is easier to be magnetized and demagnetized. So if that is the case, then that means the heat energy from the hysteresis can be reduced. Okay, get the idea. All right, wait. Okay. Okay, so this is hysteresis. Next is leakage of magnetic flux, like what you can see. Okay, flux. Okay, so the magnetic flux produced by the primary current is not fully linked to the secondary coil. So like what you can see from here. Okay, so you see primary winding, so the magnetic flux go to the secondary winding or go to the secondary coil, but a little bit go out here. A little bit go out here. Here also a little bit go out here. A little bit go out here. So this is the leaking. This is the leaking of the magnetic flux. Okay. Wait. Cao Wei, you say, does hysteresis suitable to explain the phone when charging? Sometimes phone become hot when charging. No. The phone become hot is not because of hysteresis. The phone, when you charge a phone, the phone become hot is because the battery in your phone have internal resistance. Okay, the phone battery have internal resistance. So that means when you want to charge your phone, the charge flow into the battery very fast right now in a high speed. Okay, very high speed. So that means the charge when you want to go into your phone battery, Okay, the charge, when you want to go to your phone battery, you have to overcome the internal resistance right now when you want to go in. So, to overcome the internal resistance, need energy lah, and so that energy change into heat energy. Okay, get that idea. Okay, I hope that this. Oh, okay, all right. Okay, hope this answer your question lah. All right. So go back to the. Okay, anybody got a question? Please, you just ask. All right. So let's look at the leakage of magnetic flux. Okay, so you see the magnetic flux leak out. So it takes energy to produce the magnetic flux. So if the magnetic flux leak out, so that means a part of the energy does not transfer to the secondary coil. So how to solve this problem? The secondary coil is wound. This is not wound. This is not. I know the spelling is the same, but it's pronounced differently when you mean different meaning. Okay, wound. If you pronounce it as wound, then is luka. Okay, 伤口 luka wound. But wound is the action of wounding. That means you wound the rotate like you turn something like you turn the wire, turn, and then become a coil. So you say you wound. Okay. The secondary coil is wound on the primary coil, so that all the magnetic flux produced by the primary current will pass through the secondary coil. So what does it mean? Secondary coil wound on the primary coil. So you look at this cross section. Okay, this is the actual transformer that is cut in half lah. Okay, they cut in half, so you can see that this is the iron core, and then so you see here this is the primary winding, and then outside here you see there is a secondary winding. So that means the secondary winding is on top of the primary winding, or the secondary coil is on top of the primary coil. You see or not? So if like this, that means all of the magnetic flux that is produced by the primary coil will be exposed to the secondary coil. You see or not? Straight away go to the secondary coil. So this can greatly reduce the leakage of magnetic flux. You see or not? So there are many ways that we can wound on it on top of each other. So for example, this one, core type construction. So this is the primary coil. Okay, see primary and secondary winding. So this one primary, and then this one secondary on top. Primary, secondary on top of them. So primary at the bottom, secondary on top of the. Okay, like it. Okay. All right. So any question until here? So until here we discussed all four causes for the loss of energy in transformer, and also the ways to minimize them. Remember, you do not say that it totally like it prevent. You cannot use the word like prevent the loss of energy as heat. You can say that you reduce. Okay, all of them. You say you reduce. This method can reduce. For example, this one, reduce the resistance, reduce the eddy current, reduce the heat generated from hysteresis, or reduce hysteresis, reduce leakage of magnetic flux. Okay, you must say reduce. You cannot say prevent. You cannot say avoid leakage of magnetic flux. Cannot. You cannot totally avoid or totally prevent the leakage of magnetic flux. There will definitely a little bit of magnetic flux that leak out. Okay, there will definitely a little bit of heat that is produced from hysteresis. Okay, you cannot totally say that you totally eliminate the effect of hysteresis or something like that. You cannot. Okay. Remember, if you say avoid or prevent, then it will be wrong. Wrong. Okay. Understand? That means minus mark. No mark. Okay. If you say avoid or prevent, so you have to say reduce. Okay. So anybody have any question until here? Okay, no question. Thank you very much for responding. Thank you. Okay, let's continue. Okay, next. Eddy current in induction cooker. Okay, previously when we learned about eddy current in transformer, okay, just now when we learned that, oh, the transformer got eddy current, so it causes energy loss. Eddy current in transformer is something that is no good, that's bad. But our creative scientist and creative engineer thought of a way to make use of the eddy current. So they designed the induction cooker. So the induction cooker is the stove, okay? Now this one, the stove where the stove produce changing magnetic field. The stove or the induction cooker, it does not produce heat. This is very important. It does not produce heat. It produces changing magnetic field. So the base of the pan or your pot, okay, your wok or your pan or your pot, exposed to the changing magnetic field, and the eddy current is produced. Okay, eddy current is produced in your pan. So that means when the eddy current flow in the pan, then heat energy will be produced. Okay, it will produce heat energy because the charge flow and the charge will overcome the resistance. Okay, or charge need to overcome resistance in your pan or your pot. So so work must be done. Work need to be done to overcome that resistance. So the work done will convert energy into heat energy. You see, so your pan itself is the one that produces the heat energy. The heat energy doesn't come from the induction cooker. The induction cooker produces changing magnetic field. So the changing magnetic field induces eddy current in the pan, and the pan and the eddy current, through overcoming the resistance in the pan, produce heat energy. So the pan itself that produces heat energy. Understand? So because the pan itself is the one that produces heat energy, so that means a lot of the heat energy can directly go into the food. Right? This is what we want, right? We want the heat energy. We want the energy to go into our food because we want to cook the food. So we want the energy to go into the food and not go into other places, right? So because the pan itself is the one that produces the heat energy, so most of the heat energy can go into the food. So that means this can increase the efficiency of the induction cooker. So induction cooker is a stove with a very high efficiency. Okay, very high efficiency because most of the electrical energy will convert into heat energy and go into the food. Okay, so it's also very safe also. Why is it safe? Because the induction cooker, it doesn't produce heat energy right now. It does not produce heat energy. So that means let's say that you accidentally turn on and there's nothing on top. So if your hand accidentally touch the top of the cooker, you will not get hurt because it doesn't produce heat. It only produces magnetic field only, changing magnetic field only. Okay, so the surface is not hot. The pot and pan is the one that become hot. Okay, but of course there is a disadvantage to the induction cooker got disadvantage. So what is the disadvantage? Okay, the disadvantage is that you can only use pot and pan that is made from magnetic material. Okay, made from magnetic material only. That means material that can produce induced current. Okay, affected by the changing magnetic field and produce induced current. So usually pot and pan that is made from iron, okay, made from iron. Understand? Okay, so that means other kind of pot and pan that is made from clay, made from glass, cannot be used. Understand? If your pot and pan, for example, is made from aluminium, totally aluminium, for example, also cannot use. Okay? Also cannot use because it cannot produce any current. You see or not? Okay, so that is why nowadays there are a lot of the pot and pan that they got labeled on the packaging. They will say, okay, this is suitable to be used for on the induction cooker. It's suitable for induction cooker or not suitable for induction cooker. Okay, like that. So this is induction cooker. Usually you can see this induction cooker in the steamboat shop, steamboat shop. Okay, so next. Okay, next is use of transformer in daily life. Okay, step down transformer, use notebook, computer charger, your handphone charger, photocopy machine, welding machine. Okay, step up transformer, use a microwave oven, defibrillator. You know what is defibrillator? For the first aid one, first aid where the heart stop and then charge up and then to jump start the heart again. Okay, you know that if you see in movie, the heart stop already, so they use the machine to charge and then put on the chest and then the patient, the whole body of the patient will jump up like that. That one, okay, that is that machine is called the defibrillator, okay, defibrillator, okay, X-ray machine. Nowadays, there are shopping center and some government department, they have this defibrillator in the emergency, like in the box, they put them in the wall. I think they have the box inside of this defibrillator. Okay, so it has become an important. It has become an important first aid equipment. Okay, so this is use of transformer in daily life. After that is transformer in electrical energy transmission and distribution system. Okay, this is very important. The energy transmission and distribution system is only possible when because of the transformer. Long time ago, okay, long time ago, like in I think 18 something, okay, before 1900, before 1900, transformer not yet invented. Transformer is not yet invented, but already got electricity. So the electricity that they use is direct current electricity. And because there's no transformer, so they cannot transmit the electricity for very long distance. So what happened is you will see in the city, like London, they need to build the power station in the middle of the city. Okay, in the middle of the city. Then the building around the power station can get electricity. So any building that is too far away from the power station cannot get electricity, because if too far away, then the resistance in the wire will be too high, and then the electrical energy cannot reach that region. They cannot reach because it's too far away. Okay, get either. So with the invention of transformer, electricity can be distributed to very far away distance. Okay? How? Why? Because when we step up the voltage, okay, when the power equals to voltage times current. Just now we already got discussed that for transformer, the power in the secondary coil is already fixed. So that means when we increase the voltage, the current will decrease. And when the current decreases, the power loss, okay, the power loss in the cable will decrease. You see here. At the power station, to reduce power loss, transformer increase the voltage to reduce the current. So from power equals to I square R, okay, this is the resistance of the transmission cable. This current is the current that flows through the transmission cable. So this is the power loss at the transmission cable. Okay, one more time, resistance of transmission cable, current of transmission cable. So this is power of transmission cable. This power of transmission cable means the amount of work done to overcome the resistance in the transmission cable every 1 second. So let's say if this power is 100 watt, let's say 100 watt is every 1 second 100 joule. So it means that every 1 second 100 joule of electrical energy is used to overcome the resistance in the transmission cable. Understand? Okay, so this is the power of the transmission cable. Okay, so because the resistance of the transmission cable already fixed, let's talk a bit about the resistance of the transmission cable. Maybe you would think that why need to reduce the current? Just reduce the resistance. Okay, how to reduce the resistance? Length cannot, because for example, you want to send the electricity from the power station to your house, for example, to your house, this is your house, okay, from power station to your house. It's very far away, right? So the distance is already fixed. Unless you want to build a power station next to your house, but I bet you don't want the power station next to your house. Okay. So the distance is already fixed. So that means the length of the cable, you cannot do anything. You cannot do anything to change the length. So what some more that you can do? Okay. Remember, resistance is the resistivity length over the area. So that means length, we cannot do anything about length. So what we can do is we use material with lower resistivity. And we also use a thicker cable. Okay, thicker transmission cable and transmission cable made from material with low resistivity. So this is the two things that we can do. But because of the very long length, the long distance, that means the cable become very long. Then that means the resistance also will become very high. Understand or not? So that means the resistance of the cable we already minimize as much as possible, but still the resistance is still quite big. So that means we have to do something about the current. So what is it that we can do is we use transformer to increase the voltage so that the current drop in the secondary circuit. Okay, when the current go down, then the power will go down. Okay, current increase, then the power will decrease. Okay, the power loss will decrease. Can see it? Okay, so power loss decrease when current that flows through the transmission cable decreases. So when reach the destination, transformer decrease voltage to suit application of consumer. So that means when the For example, here, okay, the power station generate the electricity at 20,000 volts. Okay, 20 kilovolts, 20,000 volts. Go to the step up transformer. The step up transformer will step up, increase the voltage until 275 kilovolts. Send to a very far place. When reach the destination already, go to the main receiving station or the main substation, and then inside the main substation, you will have step down transformer. So the step down transformer will decrease the voltage. Okay, 132 kilovolt, and then distribute in that area. So distribute in that area, go to a place that is nearer to the destination. Another distribution station with step down transformer, decrease the voltage some more, send to even smaller area, specific area, heavy industry, 33 kilovolt. Go to light industry. In the light industrial area, there will be step down transformer some more. There will be branch substation, branch distribution station of the branch substation. So the branch substation will decrease, will lower the voltage some more, and then go to residential area. There will be a small substation. Okay, usually it's like junction box, like that small electric box along every block of your taman, like terrace house, for example. Okay, one row of house, they will have one box that can decrease the voltage until 240 volt, or in this case is 230 volt. Okay, like that. You get the idea. So the transformer is extremely important in the transmission and distribution of electricity. Okay. Okay. So until here, until here, finish about the transformer. Okay, so I need to discuss one question. I want to discuss one structure question. Okay, the question that I want to discuss is number 40. Question number 40. Okay, question number 40. Okay, ready? Okay, question number 40. Okay, so let's look at this question number 40. Okay, diagram A show how electricity is transmitted from power station to a school using transmission cable and transformer. All right, so A, state one characteristic of the material that is used to make the transmission cable. Okay, so you can say that low resistivity, one characteristic of material, low resistivity. All right. Or if you say low resistance also can, but actually the best answer is low resistivity. Okay, so next here, the output power and output voltage at the transmission cable are 10 megawatt and 132 kilovolt respectively. The total resistance of the transmission cable is 600 ohm. Calculate the current flow through the cable. Okay, how do we calculate the current that flows through the cable? Okay, you see, if you want to calculate the current that flows through the cable, you need other information about the cable. Okay, so you see, the information given is 10 megawatt. Okay, it says that the output power and output voltage at the transmission cable are 10 megawatt and 132 kilovolt. And then the resistance of the transmission cable is 600 ohm. Okay. A lot of students, when they answer this question, calculate the current flow, they straight away use P equals to VI. Okay, P equals to VI to calculate. And they coincidentally can get the correct answer. Okay, coincidentally, they can get the correct answer, but they do not know what the actual reason why they use P equals to VI. Okay, so I want to explain in detail this part. I want to explain in detail. Let me throw away this part first. Okay, so you see, when we want to calculate the current flow through the cable, okay, we want to calculate current. Let's look at what are the formula that have current. We have V equal IR for current. Okay, so the information given for voltage 132 kilovolt. Okay, 132 kilovolt, and then got power, right? 10 megawatt. 10 megawatt power. And then the resistance of the cable is 600 ohm. So the formula that have current V equal IR, P equal VI, or maybe P equal I square R. Okay, so these few formula have current. So which is the suitable one to be used to calculate this current? Some students will use this. Some students will use this. Some students will use this. Okay. So those that use this will get the wrong answer. Those that use this also get the wrong answer. Okay? Let me explain why. Let me explain why. This part is very important. Okay. The reason is because this voltage of 132 kilovolt is actually not the voltage that the cable get. This is not the voltage that the cable get. So, because this voltage 132 kilovolt or 132,000 volt, if they calculate like this, 600, they will get the wrong answer. Okay? Because this voltage is not the voltage that the cable get. Why? Why is this not the voltage that the cable get? Let's look at the situation. You see, let's say that this is the power station. Okay, power station. So the power station connect to the spool. Through cable. Okay, right, this is like a normal circuit. So inside this cable got resistance, right? Not resistance 1. And then the current will flow through the spool, right? flow through the school, that means flow through the electrical appliance in the school. Okay, flow through the electrical appliance in the school. So that means the current or the charge will need to overcome the resistance of the electrical appliance in the school. And then this is the resistance of this cable. Okay, I know that okay, last time when we learned about electric circuit, we say that the cable or the wire, the connecting wire have no resistance. But in this case, we have to, in this case, we cannot say that the wire have no resistance. Why? Because the distance of the spool from the power station is very far away. And because it's very far away, that means the cable is very long. And because the cable is very long, so that means the resistance of the cable will be very high. Just like what is written in the question. You see the question straight away tell you that the resistance is 600 ohm. So 600 ohm is very big resistance right now. So we cannot just take it, just pretend that there's no resistance. Okay, because the resistance is very big. Okay, so you see, if this power station produces 132,000 volt or 132 kilovolt, and then you see this resistance in the cable and the resistance in the spool and the resistance in the cable, all of these three resistance is connected in series. And all of them are connected in series. If connected in series, what we learned in series circuit, I hope you still remember what we learned in series circuit is the voltage that the resistance get, the voltage here, the voltage here, and the voltage here, this V1 plus V2 plus V3 equal to the total voltage. Understand? That means this 132,000 volt is equal to V1 plus V2 plus V3. So that means the voltage of the cable is not equal to 132,000 volt. You see or not? Okay, I repeat, the voltage of the cable is not 132,000 volt. Okay, the spool is also does not get 132,000 volt. The spool only get a part of the 132,000 volt. You see or not? Okay, not the spool doesn't get 132,000 volt also. Okay, only a part of the 132,000 volt. That means the 132,000 volt are shared among the spool get a little bit, the cable get a little bit of the 132,000 volt. Total, all of them together is 132,000 volt. Okay, can see or not? So because like that, so you cannot calculate like this. You cannot put 132,000 volt equals to current times the current that passed through the cable times the resistance of the cable. Cannot, because this voltage is not the voltage of the cable. Okay, can see or not? This voltage is not the voltage of the cable. So you cannot calculate the current of the cable. Okay, can see. Okay, now this one, P equals to I square R, also cannot get the current of the cable. Why? Because you see the power that is given, this 10 megawatt, 10 megawatt. The 10 megawatt, if you put 10 megawatt here, mega is million, so 10 times 10 power by 6. Okay, 10 megawatt, current square resistance is 600. Also, you cannot get the correct current. Because same thing also, the power that is produced by the power station, 10 mega, 1, 2, 3, 4, 5, 6. 10 megawatt or 10 million watt is not the power of the cable and definitely not the power of the spool. this 10 megawatt also shared among the cable and the school. That means the cable get a part of the 10 megawatt, the school get a part of the 10 megawatt. Understand? Why is it that the cable also get some of the 10 megawatt? Because this 10 megawatt is energy. Okay, energy that is produced by the power station, right or not? So all of this energy, some of the energy need to be used to overcome the resistance in the cable. So that means some of the 10 megawatt is used to overcome the resistance, and then the rest will go to the school. Understand or not? Get the idea? Okay, So the power of the cable, this power 1 plus this power 2 plus this power 3 that get like the cable, power of the cable here, power of cable here, power of school, all three of them all add together equal the 10,000 volt. Equal to 10 million volt, 10 million watt. Understand or not? Okay, Okay, so the 10 million watt will be equal to power 1 plus power 2 plus power 3. But the problem here is we don't know the cable get how much of the power. We don't know. So if we don't know, then we cannot use this to calculate because we don't know how much is the power that the cable actually get, right? So same as this one, we don't know actually the cable actually get how many volt, how much volt, we don't know. So we cannot use this formula. Okay, but this one, P equal IV, P equal VI, we can use. Why? Because you see, the current that flow in the cable and the current that flow through the spool and the current that flow through this cable, they are all the same because they are all in series. You see or not? This cable and this spool and this cable, they are all in series. Because they are all in series, so that means this current, this current, this current, all the same. So, and this current is what current? This current is the total current, is the biggest current, because the current comes from the power station, right? So this current is the total current. The current that flows through the cable is the total current. So the current that flows through the cable is the total current. So this is total current. This voltage, 132,000 volt, is the total voltage, right? Is the biggest voltage. This power, 10 million watt, also the biggest power, right? So total power, total voltage, you can get total current, you see or not? So that is why we can use this formula. Total power, total voltage, you get total current. And the total current is the same as the current that flow through the cable, flow through the spool, flow through the cable here. Because they are all connected in series. Okay, So we can use P equals to VI to calculate. Okay. P equals VI. So the power is 10 mega, 10 power by 6. The voltage is 132,000, okay, 000 times current. So the current will be equal to you will get 75.7576 ampere. Okay, can see or not? Okay, so this is the current that flow through the cable. Yeah, 75.7576 ampere. Okay. Okay, anybody have any question about this this part, about how to calculate the current flow? Anybody have any question? Okay, thank you very much for responding. Thank you very much. Okay, thank you. Okay, now continue. Next is power loss in the cable. Okay, we want to calculate the power loss in the cable. So, if we want to calculate the power loss in the cable, then we can use this lah. P equals to I square R. We can use P equals I square R to calculate the power loss in the cable. Because now we have the current that passes through the cable, we have the resistance of the cable, so we can calculate the power loss in the cable. So the current is 75.7576 square. Resistance is 600 ohm. Okay, so the power loss will be 344,3528.375 watt. So you see here, how much is this? This is 3.4 million watt, right? 3.4 million watt. For your information, this kind of question, you calculate, you get the number like this. Please write the whole thing. Please, I beg you, write the whole thing. 344,3528.375, or if you want to round off also, you round off become 0.38. Okay, 344,3528.38 watt. Do not, okay, I want to stress, do not round off become standard form. Okay, I mean, don't change into 3.44 times 10 power by 6. If you change to 3.44 times 10 power by 6, it's wrong. Okay, because you round off too much. Your answer is too far away from the actual answer. Okay, so do not round off. Just write the whole thing. Do not round off. Okay, just write the whole thing. This is very important. You want the marks, you don't round off. Just write the whole thing. Okay. All right. So you see 3.4 million. Okay, 3.4 million watt out of 10 megawatt. That means the 10 megawatt come out got 3.4 megawatt lost as heat. So the rest is around 6.6 megawatt the school get. Okay, you see or not? So you can, from here, you can already see how important is the step up transformer is. Okay, if the transformer doesn't step up the voltage, okay, to reduce the current, then a lot of the energy will be lost as heat. Okay. Okay. All right. So let's continue. Actually, this is the most important part of the question that I want to discuss. Okay. Next is part C. Okay, part C. In the school laboratory, a step-down transformer is used to light up a 12-volt bulb. P, Q, and R are three different step-down transformers that can be used to step down the voltage from 240 volt to 12 volt. Table to show characteristics of those transformers. Okay, so we have three different transformers, PQR, And then the material of the core, we have iron or soft iron. And then the shape, we have shape X or shape Y lah. Okay, two different shapes lah, shape X or shape Y. And then the ratio between the primary and secondary coil, 1 to 20, 16 to 1, or 20 to 1. Okay, so based on table 2, state the suitable characteristic of the transformer which can light up the bulb with normal brightness and the least energy loss. Okay, normal brightness and least energy loss. So give reason for the suitability of the characteristic. Okay, sorry. Okay, so material of the core, we want soft iron. Okay, soft iron. Okay, why is it that we want to choose soft iron? Easy to magnetize and demagnetize. Okay, easy to magnetize and demagnetize, or least or less energy used for magnetize and demagnetize also can, or decrease heat produced from hysteresis also can. Okay, there are a few reasons that we can set. Shape of the core. Okay, you have a shape X or shape Y. So the best is shape X lah, because shape X, you see the primary coil, secondary coil, they wound together lah. Shape Y, they wound separately. So cannot help in increase the leakage of magnetic flux. Okay, so the best is shape X lah. Shape X. So reason, decrease leakage of magnetic flux. Okay, decrease leakage of magnetic flux. Next. Okay, next is the ratio. So the ratio that we want is 20 to 1. Okay, reason. So you can say there are a few reasons. So one of the reasons that you can say is you can say okay, I think the best is produce output voltage of produce output voltage of 12 volt lah. Okay, 12 volt. Or you can say can step down or decrease the voltage of 240 volt to 12 volt also can, but you cannot say that to produce step down transformer. You cannot say to produce step down transformer, or because it is a step down transformer. Because why? Because you see the Q 16 to 1 is also step down. This one 20 to 1 also step down. So if you say you choose this one because it is step down, then people will ask, why not this one? This one also step down. 16 to 1 also step down. But 16 to 1 cannot give you the 12 volt. Okay, cannot decrease 240 to 12 volt. 20 to 1 can produce 12 volt. Okay. So the best, so based on the answer, choose the most suitable transformer is transformer R. Okay, finish. Okay, done. Okay, so until here, any question? Anybody have any question? Okay, thank you very much for responding. Okay, but we still got time until 12 o'clock. Still not finished yet. I want to, so you continue, you do all of the objective question. Okay, do all the objective question. And then I want now we finish the chapter 4. I want to go to chapter 5. Okay, I want to go to chapter 5. So please get ready. I believe everybody have the note for the chapter 5 already. Chapter 5, 5.1, 5.2, 5.3. Okay, and until 6.1. Okay, you should already get. Okay, so let's continue. Okay, okay, please get ready. We want to start with chapter 5. Okay, so let's look at this topic 5.1. Okay, this topic 5.1 is a short topic. Okay, all right, so let's start. Okay, so chapter 5 is about electronics. Okay, so and when we talk about electronics, we are talking about like small electronic component, and the electronic component can work, can function because we manipulate or we apply everything that we know about electron. Okay, we manipulate, we can make the electron go in certain way. Okay, like that. So that means if you want to design an electronic component or make use of electronic component, we need to understand how the electron works or how the what is the characteristic of the electron. Okay, what are the characteristics of the electron? So in 5.1, we want to learn about electron first. We want to learn more. We want to learn more a bit about electron. So previously, what we learned about electron is just that we know that electron is very small and very small mass, and it carry negative charge, right? Okay, so we want to expand a bit what we learned about electron. Okay, now, so the first thing that we want to learn about is thermionic emission and cathode ray. Okay, thermionic emission and cathode ray. Okay, what is thermionic emission? Okay, thermionic emission is the emission of free electron from a heated metal surface. So basically, if you have a metal and you heat the metal, then the free electron of the metal on the metal surface will receive enough energy and it will be able to escape the metal surface, provided the condition is suitable. In under suitable condition, then the electron will be able to escape from the surface of the heated metal. So this effect we call thermionic emission, because the electron is emitted. Okay, the surface of the metal can emit electron through heating by making it hot. So that is why there is a word thermionic on the term. The word term here refers to thermal or heat. Okay, heat energy, thermal. Okay, so let's look at this apparatus. Okay, let's look at this apparatus. So we just go through this one. Okay, number one, there are many free electrons in a metal wire, for example, tungsten filament. When the 6-volt direct current power supply is switched on, the temperature of the tungsten filament will rise and free electron will gain sufficient kinetic energy to leave the metal surface. So thermionic emission is the emission of free electron from a heated metal surface. Okay, so if a layer of metal oxide like barium oxide or strontium oxide is coated on the metal surface kept in the vacuum tube, the temperature required to release the electron will be reduced. Okay, actually this is not very important. Okay, not very important. This is like extra knowledge. Okay, extra knowledge. Okay, so you see here, look at this thing. Okay, you see this is a tungsten filament. So the tungsten filament is connected to 6-volt power supply. So when you turn on the 6-volt power supply, okay, current will flow through, charge will flow through the tungsten filament, and the tungsten filament will become hot. Okay, so this tungsten filament will heat the cathode. This cathode is actually just a piece of metal. Okay, just a piece of metal, and this piece of metal is connected to negative terminal of EHT power supply. EHT power supply is extra high tension. EHT, extra high tension power supply. So usually extra high tension power supply is like around 500 volt to around 6,000 volt. Okay, can be higher also can be higher. Okay, 500 volt to 6,000 volt. At least the EHT power supply of our school is 500 volt to 6,000 volt. Okay. All right. So what happened is, okay, you see there are two metal plates. Okay, one metal plate here connected to the negative terminal, so we call it the cathode. And then this another metal plate is connected to the positive, so we call it the anode. All right. So you see you have two power supply. One is the 6-volt, another one is the EHT power supply. Let's say that we turn on the 6-volt only. When the 6-volt is turned on, the 6-volt, this tungsten filament becomes hot and it will heat the cathode. This number one here, heat the cathode. So the free electron on the cathode will have enough energy to escape the surface. But the electron do not just fly out aimlessly. That means for no reason just fly out. Just because it has enough energy, it will not just like fly out. Although the electron already have enough energy, but it doesn't escape yet. It only fly out when we turn on this EHT power supply. When we turn on this EHT power supply, you see this negative terminal, it will repel the electron. You see this negative, so electron will flow here, and then the cathode will become negatively charged. That means it has a strong negative charge. So the strong negative charge, it will be able to repel or push the electron that have enough energy to escape just now. And on the opposite side, there is an anode. This anode is connected to the positive plate. positive terminal. So that means this positive terminal, it will pull away electron. It will pull electron away. So this anode become positively charged. Right now, this become negatively charged. This become positively charged. So you can see here, one side repel, one side attract the electron. So the electron with enough energy due to heating will be able to fly out from the cathode and go towards the anode. And when the electron go to the anode, then it will flow lah, and pass through the mini ammeter. So this mini ammeter will show a reading. Then it will be able to show that, okay, and then you can see that, oh, got current flow when you turn on this apparatus. Okay? So you see what happened is when you reverse the connection, you see, okay, when this side is cathode, this side is anode, okay, got current flow because the electron can fly out. Okay, got current flow. Okay, sorry, this is electron. This is not current. This is electron flow. So the current is in the opposite direction. Current is in the opposite direction. This is the flow of electron, so the current is in the opposite direction. This is electron. Current is in the opposite direction. Okay. So when connected like this, a current can flow. Got current, got reading. However, if you flip it, that means if you change, this become negative, this become positive. So what happened is, this become cathode and this become anode. What will happen is, this become negatively charged, this become positively charged right now. Okay, when like this, is there going to be electron or not? Is there going to be electron fly in the opposite direction? Got electron or not? The answer is no lah. Okay, no electron will be able to go in the opposite direction. So why? Why no electron can go in the opposite direction? The reason is because this cathode is not heated. It's not heated. So because it's not heated, so the electron on the surface do not have enough energy to escape. You see or not? Do not have enough energy to escape. So the electron can only go in one direction. That means can only go from this direction to this direction. It cannot go in the opposite direction. You see or not? Okay, can only go in one direction. Okay? So that means the current can only flow in one direction through this apparatus. Okay? So this apparatus, okay, pay attention, this apparatus only allow current to flow in one direction only. This apparatus only allow current to flow in one direction. And apparatus or electronic component that allow current to flow in one direction only, we call them diode. And this diode can let current flow through thermionic emission. So we call this apparatus thermionic diode. Okay, so this thing is called the thermionic diode. Okay, and see that. Okay, thermionic diode. Okay, now, so this thermionic diode can produce a stream of electron. Okay, and produce a stream of electron. Okay, you can produce a stream of electron. Okay, you can produce a stream of electron from the cathode to the anode. Okay, produce a stream of electron from the cathode to the anode. So this stream of electron, we call it an electron beam because it is like a beam of light. It's like light like that come out from the cathode to the anode. So we call it an electron beam. Okay, an electron beam. So this electron beam or this emission come from the cathode. So this beam of electron or a ray, okay, because it's like a light, it is like light, okay, macam cahaya, 好像光, it's a light. So we call this ray that come from the cathode ray. Okay, we call it cathode ray. So this electron beam and this cathode ray is actually the same thing, refers to the same thing as a stream of electron. Okay, so we call it a cathode ray. Okay, all right. So until here, any question? Can understand how do the thermionic diode works? Okay, can understand how the thermionic diode function? Okay, thank you very much. Thank you for responding. Okay, so now that we already learned, okay, thank you very much. Thank you very much for responding. Okay, so now that we already learned, how is it that we can produce cathode ray? Now we want to learn more about the characteristic of the cathode ray. Okay, we want to learn more about the characteristic of the cathode ray. So, what are the characteristics of the cathode ray that we want to know is what happen? What is the effect on the cathode ray when we expose it to electric field and magnetic field? Okay, so what are the effect of electric field and magnetic field on cathode ray? So when we the way that we study this is we use the apparatus that is called the deflection tube, and the other one is the Maltese cross tube. Okay, so we use the deflection tube to study the effect of electric field. Okay, we use the deflection tube to study the effect of electric field. So you see here, this is the deflection tube. Okay, now you look at this part from here to here. From here to here, this part is actually the same like the thermionic diode. You see, here there's a tungsten filament. Tungsten filament connect to 6-volt power supply. So when you turn on this switch, this tungsten filament will become hot and it will hit the cathode. The cathode become hot, and when you turn on the EHT power supply, we see this cathode connect to the negative and connect to the positive. So when you turn on the EHT power supply, what happens is cathode ray can be produced. Electron beam will shoot out. Okay, a beam of electron will shoot out. Yeah. So this part to this part is the same like the thermionic diode. So this part, the function of this part is to shoot out electron. So we call this part as the electron gun. Okay, this is another name now. We also can call it as electron gun because it shoot out electron gun. Okay, shoot out. Okay, now you see here. Okay, I need to prepare. Okay, so you look at here. There's a like a screen here. This is the fluorescent grid. Why is it called a fluorescent grid? Because this piece of this plate that looks like a grid, it is coated with a chemical that can produce fluorescent effect. What is fluorescent effect? Basically, is a kind of chemical when electron with high kinetic energy strike the chemical will be able to convert the kinetic energy of the electron into light energy. So that means when the electron fly out and hit the fluorescent grid, you can see a line. Actually, the color is a green color. You can see a green. There will be a green color line that will be produced. Okay, the green color line will be produced. Okay, so this line show the place that is hit by the electron. Okay, can see or not? So when you turn on the electron gun, the electron fly out, and then you can see a green line drawn on the fluorescent grid. And for your information, the electron beam or the cathode ray, actually we cannot see them. We cannot see the cathode ray because electrons are very small right now. They are very, very small. So we cannot see. Okay, we cannot see. So we only can see or we know when the fluorescent grid or the surface that got fluorescent effect light up when got light produced, and then we know, oh, got electron fly out and hit the fluorescent grid. Okay, this anode you see, this anode, it looks like a cylinder right now. This anode looks like a cylinder. Because this anode is special, this anode is not the same like the anode just now. The anode just now in the thermionic diode, the anode in the thermionic diode is just a piece of metal. Okay, it's just a flat piece of metal. But this anode is different. This anode, it has a special structure that it can focus the electron beam. That means the electron that goes through the anode, it will be able to be focused into a thin stream, a narrow stream come out. Okay, so that is how it can draw a line on the fluorescent grid. If the anode doesn't focus, all you can see is like a thick, all green color, all green color. Okay, understand? So you can see there's a thin line being drawn on the fluorescent grid because the anode focus the stream of the electron, focus the cathode ray. Okay, to a streamline. Okay, so however, how does it work? We don't need to learn now. Okay, and you also no need to worry about what is the special, how to differentiate the different anode. We just call it anode, all of them. Okay, we just call it anode. Okay, now, so what happened is when you just turn on the switch S1 and S2, then you can see a green line like that come out. Okay, so on our observation here, record observation. So when only switch 1, switch off, switch 1, switch 2 on, then what we can see is we can see a green line. Here. Okay, then the green line like that one. at the center here. But when you draw, you don't need to draw green color lah. You just draw with your pen. Okay. Okay. Now next, switch 1, switch 2, switch 3 on. What will happen? You see, this switch number 3 is connected to EHT power supply, and this EHT power supply, this side is positive, this side negative. You see, this side is connected to a deflection plate. This deflection plate is basically just a piece of metal plate lah. So there's a plate on top and there's another plate at the bottom of the fluorescent grid. So when you turn on this switch number 3, this plate at the top will become positively charged. The plate at the bottom will negatively charged. So if we think logically, we can already guess what will happen. This cathode ray is made from electron, right? Electron is negatively charged. So the electron beam will be pushed or repelled by the negative plate and attracted by the positive plate. So what will happen is the line, the green line, it will bend upwards. Okay, we can see that it bends upwards. Okay, so when you draw that it bend upward like that. Okay, you draw that it slowly bend upward like that. Okay, so there are a few ways that if you draw a certain way, it's wrong. That means if you draw the line not logical, then it will become wrong. What are the wrong answer? Okay, what are the answers that are wrong? Okay, for example, wrong answer, okay. Okay, this is wrong answer. Wrong answer is like this. If you draw, okay, if you draw the line, the cathode ray already go in already. The cathode ray already go into the electric field, but still straight. And then only slowly turn, and then only already go in, but still straight. And then only slowly bend out like this. If like this is wrong, because the moment it go in, it must start to bend already. Understand? You cannot go into the electric field already still go straight. Like this is wrong. This one. Another is if go straight and then suddenly sharp bend up like this. This one is also wrong. Or go straight over already, only slowly bend up like this also wrong. Okay, get the idea. So it's very simple. You just think logically. Okay, you just think logically. Those lines that doesn't, if that is not logical, then definitely cannot be accepted. Okay, understand? Okay, so like this is logical. Okay, next is we reverse the extra high tension power supply. That means the positive, negative, we reverse. Okay, we change direction. Positive, negative, we change. Okay, when changed, that means the bottom become positively charged, the top become negatively charged. So what happened? It will bend downward. Okay, so it will bend downward. So we just draw like this, bend downward. And then after that, you increase the extra high tension voltage. What happened? Okay, we increase the extra high tension voltage. Wait, sorry, wait. Okay, continue. Sorry, sorry about that. Continue. Okay. So what happens if we increase the EHT voltage or the voltage of the EHT power supply lah? So we have to draw that the angle of the deflection must be sharper lah, bigger angle. That means it can deflect with a sharper angle like that. Okay, for example, this one bend until here. This one have sharper bend, can bend more like that. Okay, okay, so this is the observation of the effect of electric field on the cathode ray. Okay, very simple. Okay, so until here, any question? This is the effect of electric field. Okay, thank you very much. Thank you very much for responding. Okay, so let's continue. We make good use of the time. Okay, so next is we want to look at what will happen if we expose it to magnetic field. So the apparatus that we use is what we call the Maltese cross tube. Okay, we use the Maltese cross tube. So you look at this Maltese cross tube, the structure is about the same also. You see, from here to here, is the electron gun. That means the function is to shoot out the electrons. Okay, so the cathode is connected to the EHT power supply, and then this anode also connected to EHT power supply. But one thing that is, and then so what is the difference is, you see there in front here, there's a Maltese cross. This Maltese cross is the name of this shape. This shape is called the Maltese cross. But the object itself is just a piece of metal. Okay, it is just a piece of metal that is cut out with the shape of Maltese cross. That's all. Okay. Okay. Now, so when we turn on the electron gun, the cathode ray will come out. Okay, electron will shoot out, and this anode again. This anode is different from the previous anode. Previous anode, it can focus the electron to become a small string, but this one, the electron will diverge like this. Okay, the electron diverge in this case. Okay, the electron diverge. Okay, so the electron that shoot out, you see at the back here, there is a fluorescent screen. Fluorescent screen, that means this part, okay, this part of the glass is is coated with the chemical that can produce the fluorescent effect. Okay, it's coated with the chemical that can produce the fluorescent effect. That means when the electron hit this screen, it will light up. It will produce green color light. But because of the Maltese cross here, that means the Maltese cross will block some of the electron. So you can see there's a shadow with the shape of the Maltese cross. Okay? So that means if you look from here, what you can see is round like this, and then with the shape of the Maltese cross at the center. This is the shadow of the Maltese cross. And then here is all green color. Okay, all green color at the side. At the side is green color. Because the side is got hit by the electron. But the shape of the Maltese cross, the shadow of the Maltese cross is blocked by the electron is blocked by the Maltese cross. So that part is, there's no green light. Okay, get the idea. Okay, so now we want to study the effect of magnetic field. So we put magnet. Okay, so we put magnet. So what we do is first, okay, this is view from the front. This circle, this round is here. Because you look from the front, so it looks like this round. Understand? So what we do first is we put a magnet with north pole here. Okay, north pole here. So we put the magnet north pole here, what will happen? You see, what will happen is the electron beam will bend. It will be deflected. Okay, now, why is it that it can be deflected? This part is very important. Okay, you see, when you view from the front, that means what you see is the electron is flying towards you right now. Okay, the electron flying towards you. Okay, the electron flying towards you. So, if the electron fly towards you, that means you have current in the opposite direction. Remember, electron have charge. When the electron move, the charge move. When charge move, you have current. That means don't care whether the charge is flowing in the wire, flowing in the air, flowing in vacuum or whatever, as long as the charge flow, you have current. Okay? So current not necessarily in the wire, it can be outside like this, flying in the vacuum. Okay, flying in the vacuum like this. The electron fly out in the vacuum, in open space like this, fly out. So also got current, also got current. And when got current, what happened? Got current, the current will produce magnetic field. Okay, the current will produce magnetic field. That means when you view from the front like this, when you view from the front, the electron is flying towards you, but the current is in the opposite direction. That means the current is going inwards. This XXX represents the current. Okay, this XXX represents the current going inwards, going away from you. And when got current, that means the current will produce magnetic field. So let's say this purple color is magnetic field. Got magnetic field, magnetic field, magnetic field, magnetic field. Okay, the current produces magnetic field. So what happens is when you put a piece of magnet here with north, what happens is this north will have magnetic field come out right now. Magnetic field come out like this. Magnetic field come out like this. Magnetic field come out like this. Right now. Okay, magnetic field come out like this. So this magnetic field from the flying electron, okay, will interact with the magnetic field from the permanent magnet and will produce a resultant magnetic field. So if you still remember, the resultant magnetic field from interaction between the magnetic field from current and magnetic field from the permanent magnet will produce a catapult field. Okay, produce a catapult field. So we can find out the, if got catapult field, that means we'll produce catapult force. So by using Fleming left-hand rule, we can find out the direction of the catapult force. So for example, by using your Fleming left-hand rule, you can find out that the catapult force is upwards. Okay, the catapult force, the catapult force is upwards. So your Fleming left-hand rule looks like, okay, will look like, okay, this is your thumb. Okay, so this is your thumb. This is your first finger. And then your middle finger is like this. Okay, this is your middle finger. Okay, so this is the direction of the catapult force. This is the direction of the magnetic field. This is the direction of the current. So you see the current going in. This is the direction of magnetic field. The force is upwards. So the catapult force is upwards. Huh? So this upward catapult force will act on the string of the electron. That means will act on the cathode ray and make the cathode ray bend upwards. So when the cathode ray bend upwards, that means the shadow will also go up. Lah. That means what you see is the shadow will go to the top like this. Okay, the multis cross will go up lah, like this. Okay, so you can also do the same thing. You can also use Fleming left hand rule to find out lah what happened to the magnet. You put like this. This one north, this one south, this one south, this one north. North here, south here, south here, north here. What will happen? Okay. So let's say this one. Okay, north at the top, south at the bottom. So the magnetic field go downward, the current go inwards. So the catapult force will be to the left. So you can see that the multis cross the shadow of the multis cross will be to the left. Lah. This one flip, so it will be to the right. Okay, this one will be bottom, and then this one go to the top. Lah. Not same as this one. These two same. Go to the top. So this one is at the bottom. Okay. So this will be the effect of the magnetic field onto the cathode ray. Okay. So until here we learn that the electron, when provided enough energy through heating, the electron can escape from the metal surface, and it will be able to bend when exposed to electric field and magnetic field. Oh, and one important thing that I forgot to mention is you see this multis cross tube. You see vacuum. Inside here is vacuum. Okay, the thermionic diode inside here also vacuum. Okay, and then the deflection tube also vacuum inside. So it's very important for this apparatus. The inside is vacuum, because if inside is not vacuum, if got gas or air, what will happen is it will block the path of the electron. The electron cannot have a clear path. Okay, get the idea. The electron cannot get a clear path. So that is why the inside of all of this tube, it must be vacuum. Okay. So today we cover until here, until the effect on the cathode ray, and then the rest we will continue tomorrow. Tomorrow continue a little bit, and then we can go to the next topic which is semiconductor diode. Okay. So anybody got any question? Okay, so if no question, then today we stop here. Okay, thank you very much.